Okay, good afternoon, everyone. Welcome. My name is Frank Schnelle. I'm a product manager for current sensors at Vakuumschmelze, and I'm excited to present you today our new lineup of open-loop Hall-based current sensors for industrial applications. For those of you who do not know us yet, Vakuumschmelze is deeply rooted in the development of customized solutions for both the soft magnetic and hard magnetic domain. And we are going to celebrate our 100th birthday in July this year. This slide gives you a brief overview of our focus applications. You see that we span a rather large area in the industrial landscape. We have solutions for renewables, so you see the energy transformation there. You see aerospace, especially electric flight, that is gaining a lot of traction nowadays. We see the automotive solutions and also scientific solutions. But today we are going to focus on this new sensor series that is focused on industrial automation. This slide here gives you an overview of our production footprint. We are headquartered in Hanau, in Germany, near Frankfurt. This is also where we produce our magnetic materials. But we also have production sites in Slovakia, in Finland, in Malaysia, and in China. And this is accompanied by a large network of sales representatives across the globe. For those of you who already know us, we are coming from closed-loop current sensors. So the majority of our current sensors that we have at the moment are based on the closed-loop principle. And in the upcoming slides, I'm going to contrast the closed-loop design principle with the open-loop approach. If we take a look at the closed-loop sensor, you see here that we have a kind of feedback loop in the sensor. The idea is that in the sensor, we have an additional coil that drives a compensating current that will compensate the magnetic flux that is generated by the primary conductor, so the signal that we want to measure. This will be compensated by this compensating current, and accordingly, the magnetic flux in the magnetic core will be driven to zero. And in the air gap that you see, we have a magnetic flux gate probe that is detecting the state of zero magnetic flux in this air gap. And once that this is the case, once that the magnetic flux is zero, then the compensating current is giving the output signal and tells you what primary current is flowing at the moment. This is the principle of a closed-loop sensor. If you contrast this now with an open-loop design, there you have a slightly different setup. We obviously again have a primary conductor that is generating a magnetic flux that is concentrated in the magnetic core. But now in the air gap, we directly have the Hall sensor, the Hall IC, for a direct magnetic flux detection in the air gap. And then the output signal is directly the measured magnetic flux and directly relates to the primary current. We can now compare both sensor types qualitatively in terms of accuracy and size. If we look where we would place the closed-loop sensors, they are basically located at the top in terms of accuracy. So if you're looking for the highest possible accuracy, closed-loop sensors are most likely your best bet. And if we contrast this now with the open-loop sensors, they come at a slightly reduced accuracy, but as a trade-off, a much smaller size. We will compare both in the next slides. We see here the accuracy diagram of a typical closed-loop sensor. This is one of our sensors from our existing closed-loop lineup for measuring 100 amps. And you see here on the vertical axis, you see the deviation, so the relative error. And on the horizontal, on the x-axis, you see the primary current. And this pole-like behavior around 0 is expected because for the relative accuracy, you basically divide by the flowing primary current. But what is remarkable here is the relatively flat curve, the flat accuracy over the measuring range. And you also see that the relative accuracy that is achievable by the closed-loop design is very high, so the error is low in contrast. Yeah? So you see the relative deviation is in the order of 0.5 percentage points, so a very low error. If we compare this now with the new open-loop current sensor series that we are introducing here, you see that the diagram is a bit different. You see that the relative accuracy is, so to say, increasing a little bit earlier when going to 0, but is still below 2%. Yeah? So this is, so to say, the accuracy trade-off that you make. Yeah? If you do not need the highest precision, then the open-loop current sensor is a viable solution. And you get one benefit, and this is just qualitatively shown here. This is not a drawing to size here, but you see when you compare the closed-loop sensor to the open-loop sensor, you can get up to 80% of size reduction. So you basically always have to make this trade-off, accuracy versus size, when deciding whether to use a closed-loop sensor or the open-loop design. Let me now briefly touch the major applications that we see for this new family. So on the top here, you see an application or a general diagram for applications that are driven by a DC source. So basically a battery. This could either be a battery energy storage system, for example, or it could be an uninterruptible power supply, as indicated here. And then the new open-loop sensor would be located between the battery and the DC-AC inverter. On the AC side, you then basically have your electrical load. This is one scenario. Another potential scenario is for electric drives application. There you obviously have a AC input, for example, a 3-phase AC grid input. You have an AC-AC inverter. And then the closed-loop sensor is, open-loop sensor, I'm sorry. The open-loop sensor is located between the inverter and the motor in this application example. And we are talking about application classes in the range of 30, 40, 50 kilowatt, for example, where these sensors are suitable. And here you see the overview, what we are offering. So this is brand new. We are introducing this new lineup here on the trade show. We start the new product line with 3 variants for 80 amp nominal current, 100 and 120. They all are supplied by a +5 volt power supply. And as already shown, the major advantages is the extremely compact size and footprint. And the Hall IC is based on a partnership with Allegro. So it's a state-of-the-art, latest industrial Hall IC technology that is integrated in the sensor. And we offer then, with this design, 2 further benefits that we will touch upon right now. One is the frequency bandwidth, and the other one is the response time. Both we will see in a minute. First, I will give you just an idea how the sensor is designed, what we have. So you see we have a silicon iron-based magnetic core that is doing the flux concentration. We have a robust casing with an integrated bus bar, and we have chosen a plastic material that is free of red phosphorus flame retardant material. And you see the state-of-the-art Hall IC. And this is now brought together. We should see this here. This is integrated in the sensor and combined to this extremely compact footprint and volume. Let us now take a look at a measuring curve. Here you see the frequency response. So we have the frequency on the horizontal axis and the magnitude in decibel on the vertical axis. And you basically see that we have an extremely flat frequency response over a rather wide range. So we say here flat response up to 200 kilohertz, but actually you can already see in the diagram that there is still some headroom for even higher frequencies. So it is really a very flat response, giving you benefits when using modern semiconductor solutions like silicon carbide or gallium nitride, where you typically have higher harmonics that you can still measure with this design. And the technical advantage of this flat response is basically also seen in the response time. So what we see here in this measurement is basically a current step where the primary current basically steps up. And you see here how the sensor output, the voltage output follows. We see this here a little bit larger. Just to give you an idea how this concept works, you see the primary current that is ramping up and the output of the sensor, and this time at 90% of the current step is the response time. And for this new open loop sensor series, the response time is smaller than 1.5 microseconds in this scenario. And this means this sensor is also ideally suited for applications where the primary current is changing rapidly, like for example in UPS applications. Yeah, and finally I would like to invite you to visit our booth in Hall 7, just the next hall, in booth 121, where we have the new family presented, where you can take a look at actual samples and see the size of this new solution. Thank you very much for your attention.